Welcome to this IPMI 2021 presentation. My name is Raghav. I will be presenting our work on segmenting two-dimensional structures with strided tensor networks. This is joint work carried out with Erik B. Dam and Jens Petersen at the University of Copenhagen. So when we have data such as this, so it's a two-class classification in two-dimensional data. So the data is not linearly separable. So in such cases, you are striving to obtain a nonlinear decision boundary. And neural networks form sort of like the overparameterized class of models, which are highly nonlinear and which have been used extensively for wide-ranging applications now. And now the strength of something like a neural net is that you can learn features to be able to in a low-dimensional space, so that you can perform these nonlinear decision boundaries quite well. On the other hand, so the same two-dimensional data could be lifted into a higher dimensional space, such that the data becomes linearly separable. Now, this has been the trick that has been used as the kernel trick with support vector machines. And predominantly, these classes of methods have used very simple feature crafting. So what are tensor networks? So tensor networks are learnable approximations of linear models, and they operate in exponentially high dimensional spaces. So now, more formally, tensor networks are, if you were to take a higher order tensor, then you can factorize with a network of lower order tensors. And this formalism is what tensor networks are. We will be looking at one of those tensor networks quite closely. So what is the advantage of using tensor networks? So they can very efficiently approximate higher order tensors. Efficiency comes both in terms of the number of parameters used to represent and also the computation. So, and the parameters that are used to approximate higher order tensors can be learned. So this is where sort of the automatic differentiation, sort of a way of learning this approximation comes about. So now, where are tensor networks used currently? As the name suggests, like it started out with predominantly in quantum wave, in studying quantum wave functions, where the particle entanglements could be very, efficiently modeled using tensor networks. Now, since then, it has also been used for data compression. And within sort of the machine learning neural network literature, it has also been used to explain the expressive powers of neural networks, to compress neural networks, and also quite successfully in supervised machine learning. And a more relevant application for this venue is in the last year. So we actually adapted tensor networks to perform medical image classification. So it was presented at middle last year, and it won a best paper runner-up award even. What are we trying to do with this work? So the tensor networks are still a novel class of methods for supervised learning. They have been around for 4 to 5 years, but they've been used very in a limited sense. So now we want to kind of adapt these tensor networks and explore if they can be meaningfully used for image segmentation, as there aren't any, to the extent that we are aware of, literature on tensor networks for image segmentation. So what do we then, at a high level want to accomplish with this work? So we're trying to approximate linear segmentation models operating at exponentially high dimensional spaces. And this we try to do using quantum tensor networks. Now, this is sort of, in a classic supervised, learning setup. So we have the input, and then we have the target labels, and then we want this task to be, performed by a tensor network-based model. Now, here's like a very quick introduction to tensor notation. We won't actually be using a lot of tensor notation, except for in a small portion, but I will try to very quickly emphasize what the most important aspects. So it's a graphical notation, sort of a shorthand for writing out tensors of different orders. So the edges, dangling from these nodes basically indicate how many orders or what dimensions they are. So for instance, a scalar does not, it's an order 0 tensor, so it does not have any edge. Then a matrix has 2 edges, and then a vector has 1, etc., etc. So also consistent with the tensor notation, so the indices of the tensors are provided or written out as the superscript. So for instance, this order 3 tensor, or let us look at, so this order 3 tensor M and P. Here we are trying to show the dot product between the two. So that is written as Mij(k) and then Pij(k). So now the distinction here with the superscript and subscript is that the indices which are subsumed in the operations which are added over, then they are as written out as subscripts, whereas the indices that are retained after the operation are usually written as superscripts. So now here, for instance, the dot product between these two order 3 tensors is written as in a graphical notation as this. So these edges are where the summation is performed over. So these indices are subsumed. In the end, you get a scalar output here. So now let us move on to image segmentation. So a classical image segmentation decision rule would be written as something like this. We have a C-channel image with H times W, two-dimensional image, where each pixel is a real number. Then we want to learn a function which takes the input and then gives us an output. And if we are interested in a multi-class segmentation, so then we are still in the image space, H times W, in terms of the spatial resolution. And each of the pixel either has a label of 0 or 1 corresponding to the different M classes. So now the parameterization of this mapping is usually written out as theta. And then if you're using a neural net, then these are the parameters of your neural network. Now, how is this different in this particular cases, in this particular work? So with tensor nets, what we are trying to do is we first lift the data into a really high dimensional space, which we will see how it is done, so that the model itself is constrained to be linear. So this is sort of because tensor networks are sort of linear models. So we try to see how this can be done. So in some sense, can we lift the input data to sufficiently high dimensional space such that we can learn a linear decision boundary so that we obtain segmentation result out of that. So now what about these high dimensional feature maps? So this is basically done in 3 steps to be able to use tensor nets. So the first step is that we take the 2-dimensional image and then we flatten it out into a 1-dimensional vector. So which results in this vector which has n pixels. And each of these pixels is then what is known as, we apply a local feature map to each of these pixels. Now, this is sort of similar to the feature maps that are done in SVMs or in other kernel methods. But here, it's a very standard, non-parameterized model, the transformation here. As you see, these are just sinusoids, and then there are no additional parameters. So this is looks a bit complicated, but then it's only to take every pixel and then transform it into a d-dimensional, pixel map. So another thing that we do here is that we normalize the intensities to be between 0 and 1, and then each pixel is now from a scalar to be lifted to d-dimensional space. So we have performed a local feature map here. Now, for instance, if you take d equal to 2, we just end up getting a sine and then a cosine operation at this intensity values. Now, why is this done? So this is sort of inherited from sort of the physics literature, but then it has some interesting properties that, of course, if you were to go and then look at this, the norm of this transformation is unit norm, and that will have a significance in when we do the joint feature maps. So now, once we go from, we take each pixel and then learn a d-dimensional local feature map, not learn, transform it to obtain a d-dimensional feature map. Then we take these local feature maps and then perform a tensor outer product. Now, what happens when we do the tensor outer product is that this d-dimensional local feature maps are lifted to d to the power n-dimensional feature map. And that the local feature map had a unit norm also ensures that the joint feature map also has a unit norm. What do we do once we have lifted the data into a high dimensional space? We try to learn a classification rule. Now here, it's basically something like a pixel classification rule. So now here comes the weight tensor. And then we see that it's not nonlinear. We're just basically taking the joint feature map and then performing a dot product. So this is sort of the classical linear decision boundary. Now, as I previously said, the subscript indices are the ones which are summed over, and then the index that remains is the output index of the tensor. So now after this operation, we end up with a vector which has the index m, and it is of dimension n. So meaning we started out with n pixels, and then now after this dot product operation with the joint feature map, we end up with an output which is also a vector of length n. Now, in a graphical notation, this is indicated like this. You have the weight tensor, which is order n plus 1. If you see, these are the n edges corresponding to the n input pixels, and then the additional output edge. So this is an order n plus 1 tensor. And then these are the edges along which the summation happens, so that in the end, we're just left with this one index m, which is of dimension n. But there are a couple of problems here. So one is that this dot product in equation 4 is intractable. Now, why is that? So let's take a very simple example. If you take a 16 by 16 input image, which is on the very low end for what we would deal with medical imaging, and then we only perform a local feature map of d equal to 2. So it ends up, we end up with number of parameters in this theta is 10 to the power 79. And just to put that in context, the number of atoms apparently in the observable universe is 10 to the power 80. So this is in no way doable. And then the second thing is that because we took the two-dimensional feature map and then flattened it into one-dimensional vector, if you're trying to perform image segmentation, we're throwing away a lot of useful structural information, because segmentation it has like a lot of local behavior. So where a neighborhood would be most useful in making the decision about if a pixel belongs to the foreground or the background class. But by flattening out a two-dimensional image, we lose all of that spatial correlation. So how do we overcome this? We take up two approaches to alleviate the two aforementioned problems. One is that we, of course, the dot product cannot be computed because it's intractable. So we approximate it with a type of tensor network called the matrix product state, which I will elaborate in the next slide. And the other trick that we do to not lose, all of the spatial correlation is, instead of working in a full high-resolution image, we start operating on smaller patches. Now, we will see how this helps. We only look at non-overlapping patches. So we basically take the image and then patch it up and then apply MPSs on all of those individual patches. Now, this is sort of the overview. So then once we have the input image, and then we have an MPS, which acts here representatively on this k by k smaller region. And then, as if you were to do weight sharing, we move this, stride this across the image in non-overlapping patches so that we get the predicted segmentation. And then we can perform classical supervised learning and then learn the parameters of this MPS using backpropagation. So how do we use MPS, the matrix product state tensor network, to approximate the dot product? So this is a class of approximation methods, and it's also known as the tensor train networks. Now, the key idea is to take a higher order tensor and then approximate it with into a chain of order 3 tensors. Now, how is that done? Basically here. So now, there's a couple of parameters here which I will walk you through. So if we have an order n tensor here, so we approximate that with lower order tensors. If you see, each of these A's has at max only 3 indices, meaning these are only order 3 tensors. So now once we sum over all these subscript indices, what remains is only the superscript indices, and these superscript indices match the index of the input tensor. So, and what is beta? So the subscript indices along which the summation happens can be of a particular dimension, and that dimension controls the quality of approximation, and that is called the bond dimension, denoted here as beta. So once we have used the MPS to approximate our linear decisions in high dimensional space, so the other aspect was to overcome the loss of spatial correlation. And that is performed by using simple non-overlapping patches and then flattening them. Now, this also has an advantage in computation, because once you have a patches, you can batch them and then do parallel processing, because we are anyway performing weight sharing. And this one could think of as being similar to if you had a strided convolution, and then where we are doing basically the same kernel is being used across different parts of the image. This is something along those lines. So now the final tensor network with our two approximations, one is by using MPS and then using patches on k by k strides, yields us basically we have a single MPS which is operating on a small patch of the image, which is k by k. So we obtain the final model. So and this can be trained with backpropagation, assuming we have access to a label data set. Coming over to the experiments, so we present evaluations on two data sets, sort of slightly diverse. One is histopathology images for multi-organ nuclei segmentation. And then each of these images are 1,000 by 1,000 pixels. And we have access to 30 training images, which were used also. A subset of it was used for validation, and then a holdout test set, which comprised of 14 images. Now, for the chest X-ray images, these were aggregated from the Shenzhen and Montgomery hospitals. Each of these images were originally of high resolution, but they've been scaled down to 128 by 128. And then we have access to about 528 training validation images, and then 176 for test. So we compare these the performance of our proposed segmentation model with a 2D unit, a tensor network which does not operate on patch levels, and then a multi-layered perceptron. So the two hyperparameters for the proposed tensor net are basically the bond dimension and then the stride length. Then we, in the paper, describe how we choose these methods, how we choose these parameters, and then we end up with beta equal to 4, and then the stride length being 8. And then for the chest X-ray images, we use a beta of 20, and then a larger stride length. And the local feature map is set to 4. The models were implemented in PyTorch, and then we use a vanilla Atom optimizer. The performance itself was compared using DICE, and then the PRAUC, the precision recall area under the curve. Now, for the nuclei segmentation data set, so we have the strided tensor network, which is ours. Then there's the 2D unit, then the MPS, the tensor network without patching. And then we also evaluated it on a standard 2D CNN, a fully convolutional network. And I mean, the most interesting result are, for instance, to give a context, it's with the 2D unit, which was also tuned for hyperparameters. And then the best performance that we ended up was for the DICE, which was, I don't think there's any significant difference here between the two. And then in the PRAUC, it's about, I would say that the strided tensor network is in the same ballpark as a unit. If you were to see, there's like the number of parameters that the tensor network uses is 2 orders magnitude less. And I will have a bit more to say about this later on. For the chest X-ray images, so the models, again, are in the same ballpark. Like our model is able to perform as well as a 2D unit. Yeah, so and I here we also compare it with like an MLP, just to also tackle the idea of if you were to flatten the image and then put it through an MLP, what happens? What about some qualitative results? So as we see that the MPS, without doing the patching, basically does not have any context of the global structure itself. So there's sort of an average segmentation that is learned, which is also something similar we observed with an MLP, because the pixel correlation is lost. Whereas with the UNet, which is actually operating on 2D input, and there's our tensor network, which operates on smaller patches, we don't see this drastic of an effect. So to summarize, we proposed adaptations, modifications to how a tensor network could be used to perform 2D image segmentation. And this, to the extent that we are aware of, is the first use case of tensor networks for image segmentation. So we address the challenges by using weight-shared MPSs on non-overlapping image patches. So the model has only two hyperparameters, the bond dimension and then the stride length, which can be sort of grid searched, or smarter ways of optimization can be done. So another sort of a consequence of having the TensorNet is that it has lower memory footprint, and that's because of there's only a contraction operation. So there's only a forward, there are no intermediate feature maps as such stored in these tensor nets, and this means the memory footprint for these models can be lower. And if you come to think of what an MPS basically does, it's a single sort of a filter which is acting on different parts of the images. Now, we speculate that this could be thought of, from like a CNN point of view, as if we're not learning banks of filters, but then just a single filter which is able to perform, segmentation. So do visit us in the second poster group. And the data and the model for this work is available at this link.